Section 14.5, temperature and rate. Rates of most chemical reactions increase as temperature rises. For example, dough rises faster at room temperature than when refrigerated. Plants grow more rapidly in warm weather than in cold. Make sure that you have these notes out, section 14.5, temperature and rate, as we go through and answer some questions and give some notes about how temperature affects the reaction rates. First of all, there are two tenets that help describe how temperature affects the rate of a reaction. And the first one is something called the collision model. The collision model we actually studied back in chapter 10 when we studied gas laws. And the main tenet of the collision model is that molecules must collide to react. Which kind of makes sense. They got to bump into each other to react. If they don't bump into each other, they're not going to react. And therefore, as you increase the temperature, you generally increase the pressure. And the pressure, of course, has all to do with collisions of molecules. And so what holds true for gases in this case also holds true for liquids and in most cases solids as well. That is, you increase the temperature, you increase the bump into itness of the molecules and increase the reaction rate. Secondly, why isn't the collision frequency the only factor affecting reaction rate? Well, the second factor that affects reaction rate is something called the orientation factor. And the orientation factor says that when molecules collide, they have to be orientated in a certain way for the reaction to occur. If you take a look on page 594 of your textbook, I'll put it here in front of the camera. The bottom of page 594, they've got a couple of really nice pictures. And this is the 10th edition of the textbook. You can see in this particular reaction, one molecule or one atom actually bumps into another. And when the collision happens, it splits, and you can see we've made two new things. But in the bottom one right here, if it collides and doesn't hit the other little green atom inside this molecule, you can see that nothing happens. It collides, but it doesn't cause the production of two new molecules. And so the orientation, the way they bump into things, happens to be a real important factor as well. So just increasing the temperature alone, including increasing the number of collisions, doesn't necessarily mean that you're going to increase the reaction rate. The second is the orientation factor, the way that you bump those in together. There's a graphical way that we can represent the progress of a reaction and the amount of energy that needed, and therefore the energy needed that can cause a reaction to happen and cause this rise in temperature and this orientation factor to be graphically represented. This is called an energy profile diagram. The vertical axis of an energy profile diagram is the energy, and the horizontal axis is what's called the reaction pathway, many times analogous to the time that it takes for a reaction to occur. And since energy is directly, or kinetic energy anyway, is directly proportional to temperature, lots of times we can say that the temperature is as the temperature is increased, the kinetic energy moving those molecules is increased. And so we can look on a y-axis right here, or a vertical axis, and say, hey, if we increase the temperature, we're going to increase that energy. If you look at this graph just for a second, though, you can see that as we increase the kinetic energy going to the right, as we increase the energy going to the right, we increase the fraction of molecules that obtain this minimum energy needed to reach the reactivity. This minimum energy needed to reach The reactivity is called the activation energy, symbolized by E sub A, where A stands for activation and E, of course, stands for energy. You can see at a higher temperature, it actually smushes the curve down, and more molecules break this dotted line barrier right here and obtain that minimum amount of kinetic energy needed to initiate the chemical reaction. So you can think of that as one way that temperature can graphically be represented as causing more energy to be produced in those molecules, and therefore causing the energy to the reaction to take place. Let's look at an actual energy profile diagram. This is not an energy profile diagram. This is just a graphical representation of how temperature can affect energy. This reaction profile diagram right here symbolizes a number of different things. First of all, this is where we start with an amount of energy. It happens to be, this is a reaction pathway for the conversion of diamond to graphite, and so it's got diamond written right here. And this is the initial amount of energy that the molecules start with. As we attempt to initiate the chemical reaction, you need a certain amount of energy right here, this peak right here, and listed by this arrow right here, to initiate the chemical reaction. This is called the energy of activation. This energy of activation could be anything from like a spark from a match. It could be just like a little push or a shove of a molecule in the right direction because of the combining characteristics and increase in pressure. It could be a number of different things. I like to think of it lots of times as like the spark from a match that initiates the burning of something. This height right here, measured from the initial energy to the top of this reaction profile curve right here, is called the activation energy, and it's symbolized by E sub A. Once the reaction starts to occur, though, you can see that this reaction loses a lot of energy and eventually produces graphite. And this distance from the start to the end right here is the enthalpy of the chemical reaction, the delta H. And you can see right here that the ending energy is much lower than the beginning energy, and so we'd say it has a negative delta H, or it's an exothermic type process. An exothermic type process. So you can see this right here measures the energy of activation. This right here measures our enthalpy of the chemical reaction. Let's take a look at a series of these reaction profile diagrams right here at the top of the next page. And it says, consider a series of these reactions having the following profiles. You can see right here the activation energy is measured on each one of them. And then you can also see the enthalpy of the reaction measured in each one of them as well. Assuming that all three reactions have nearly the same frequency factors, rank the reactions from slowest to fastest. Well, first of all, the lower the activation energy, we can assume the faster the reaction. So if we take a look at each one of these, this one has an activation energy of about 15 kilojoules per mole, this one 25, and this one 20. So we would generally think that the lower the activation energy, the faster it would go. So we'd say 1 would be the fastest, and then we'd say that 3 would probably be the next fastest, and 2 would probably be the slowest because it takes the most activation energy to get going. So 2 to 3 to 1 would be from lowest to highest, slowest to fastest. This would be the fastest, this would be the slowest. And it says, imagine that these reactions are reversed. Now rank the reverse of the reaction from slowest to fastest. And if it's the reverse of the reaction, that means we'd actually start right here, and we could actually draw a dotted line right here, and our activation energy would be from the bottom to the top. And so in this case, it would have an activation energy of 25 kilojoules per mole, 10 plus 15. For this one, we'd be starting way down here, and it'd be 15 plus 25, or 35, 40 for an activation energy right there. And then this one actually is an endothermic process. You can see it actually has a positive enthalpy. And so for this one, the reverse of the reaction, instead of being 20 kilojoules per mole, it would be approximately 15 or so kilojoules per mole. So we'd think our fastest one now would have the lowest activation energy, and it'd be 3. Our second fastest should be 1, and our slowest would be reaction number 2. So fastest, slowest, because it has the lowest activation energy. Well, Svante Arrhenius, a chemist back at the late 1800s, noted that for most reactions, the increase in rate with increasing temperature was nonlinear. He developed an equation called the Arrhenius Equation that related 3 factors that affect the rate of a reaction. These 3 factors were the fraction of molecules possessing the activation energy, the second one was the number of collisions occurring per second, and thirdly, he looked at the fraction of collisions that had the appropriate orientation factor. And he put these 3 factors together into one equation. And the equation that he came up with, called the Arrhenius Equation, said K is equal to A times e to the negative E sub A divided by RT. Well, A was something called the frequency factor. So that took into the account the number of collisions per second. And it varied. It varied a little bit, but it was fairly constant throughout most temperatures. And of course, it varied depending on the molecules, the types of molecules that were reacting. K was the rate constant. T was the absolute temperature, the Kelvin temperature, and E sub A was the activation energy. Well, anyway, when you ended up taking the natural log of both equations, the equation became a little bit simpler to look at. And it took this form. Natural log of K was equal to negative E sub A times 1 over RT plus the natural log of A. Now, if you take a look at this equation set up after the natural log was taken, and you're a little bit observant, you can see that this is y, this is equal to m, this is equal to x, and this is equal to b. And so it takes on the form, once again, just like some other equations we've looked at in this chapter, of a line, where the y-axis is the natural log of the rate constant. The x-axis is 1 over temperature times a constant, which is the gas constant right here, R. I guess I forgot to say that up here. R is the universal gas constant at 8.31 joules per mole Kelvin. And then B, that's the y-intercept, of course. But look at what the slope can tell us. The slope can tell us the energy of activation. And so you can, by graphical analysis, determine the activation energy for a reaction simply by knowing the rate constant at several different temperatures. And lo and behold, we've got a sample problem like that. Look at this. The following table shows rate constants for the rearrangement of a chemical called methyl isonitrile at various temperatures. And so we have temperature and rate constant data. From these data, calculate the activation energy for the reaction and what is the rate constant for this critter. Well, the first thing what we need to do is to get some other data. Because when you have to graph this, remember that to find the activation energy, you technically graph the natural log of the rate constant versus the inverse of the temperature. And so down here we have natural log of the rate constant, and right here we have the inverse of the temperature, all tabulated very nicely for us. And believe it or not, look at this. Here is the natural log of the rate constant, and here is the inverse of the temperature on the horizontal axis. And then we have a really nice graph of that, and all our job then is to find the slope of this line. And slope, remember, is equal to change in y divided by change in x. And if you pick a couple of points off of here, they picked a point somewhere right here. You can maybe see this little line right here, and then they picked another point right down here in the sample problem. And if you plug in those numbers, you've got negative 6.6 minus negative 10.4 for a change in the y here and here, and then that's divided by the change in the x-axis, which is approximately 0.00195 minus 0.00215. And when you do that subtraction on your calculator and you divide it out, you get the slope, remember, is equal to negative E sub A divided by the universal gas constant R. And so after you solve here now for E sub A, after putting in the number for the slope, E sub A is equal to the slope times R, which turns out to be 1.6 times 10 to the second, and that happens to be in kilojoules per mole. You have to be real careful about the R here to make sure that it's in kilojoules per mole Kelvin, which means that it's not 8.31 anymore, but 8.31, I'm sorry, 31, converted to kilojoules instead of joules. Anyway, the point is not that you can tabulate all this and put it in your calculator and have it graph it and find the slope for you, but that you understand that the natural log of the rate constant versus the inverse of the temperature will allow you to get a straight line, that the slope is a very easy way. Well, it didn't look so easy, but eventually it is pretty easy to find the activation energy from it. So what is the sign of the slope on the graph line above? Well, it's negative because it's going backwards like this. What quantity is on the vertical and horizontal axis? Well, the natural log of the rate constant is on the vertical axis, and then on the horizontal axis, remember, it's 1 over temperature, the inverse of the temperature. And then lastly, what data was collected to determine the activation energy? Remember, it was temperature and rate constant data. You simply need to memorize that. That's what Svante Arrhenius' equation was. His equation is given on the crappy periodic table, and so you can refer back to that to give you a hand with it as well. So understand the relationship between rate constant and temperature. You will win a prize. Good luck with your chemical kinetics and temperature problems.